Hola, my name is Pamela. Welcome to my channel. Today I'm gonna talk about pH is a measure of the acidity or alkalinity of water with dissolved chemical compounds. Its expression is given by the logarithm of the inverse of the H ion concentration expressed in moles per liter. Note that pure neutral water has a hydrogen ion concentration of 10-7 moles per liter. Then, the pH will be calculated with the result of the second formula. An acidic solution has a higher hydrogen ion concentration than pure water, and therefore, its pH will be less than 7. The reverse is true for a basic solution, and its pH will be greater than 7. Practical measurements of pH are between the values 0 to 14. In this table, we can see the concentrations of various types of solutions with their corresponding pH. Various methods can be used to measure pH, among which the most accurate and versatile for industrial applications are the glass electrode system and the transistor ISFET system. ISFET stands for Ion Sensitive Field Effect Transistor. The glass electrode consists of a glass tube closed at the bottom with a glass membrane especially sensitive to hydrogen ions. In the internal part of this membrane, there is a buffer chloride solution of constant pH, within which a silver thread coated with silver chloride is immersed. Although the mechanism that allows the glass electrode to measure the hydrogen ion concentration is not exactly known, it is established that when the electrode is introduced into the liquid, a potential directly related to the hydrogen ion concentration of the liquid is developed. That is, if this concentration is greater than that inside of the electrode, there is a positive potential across the electrode tip, and if it is less, the potential is negative. This potential changes with temperature. For example, it goes from 54.2 millivolts at 0 Celsius to 74 millivolts at 100 Celsius per pH unit. To measure the potential developed in the glass electrode, it is necessary to have a second element or reference electrode in the solution. This, apart from closing the circuit, supplies a constant potential that serves as a reference to measure the variable potential of the glass electrode. The reference electrode contains an internal cell made up of a silver wire coated with silver chloride in contact with a potassium chloride electrolyte. This electrolyte passes into the sample solution through a liquid junction. In this way, the internal cell of the electrode remains in contact with a solution that does not vary in concentration, and therefore provides a stable potential reference. Here, we can see the internal arrangement of the electrodes and the potentials they measure. The existing potentials are the following. E1, potential between the internal metal electrode and the buffer solution that can be considered constant for a given temperature. Extremely high temperatures can lead to dissolution of the silver chloride coating on the electrode. E2, potential drop between the inner electrode and the inner face of the glass membrane that can be considered negligible. E3, potential between buffer solution and glass membrane surface that is constant due to the stability of the buffer solution and the glass membrane. E4, potential drop across the membrane that remains constant for short periods as long as the glass membrane does not suffer alterations of chemical or mechanical origin. If this potential drifts, it is calibrated with a buffer solution of known pH. E5, potential between the outer surface of the glass membrane and the tested solution that varies with the concentration of hydrogen ions pH of the tested solution. E6, potential drop across the tested solution that is considered negligible, except in the case of poorly conducting water or non-aqueous solutions. E7, represents the liquid junction potential between the tested solution and the reference solution. Its value is negligible, although clogging or excessive external pressure against the joint can influence in the measurement. E8, the potential drop within the reference electrode is negligible. E9, contact potential between the reference electrode and the CIK solution that can be considered constant if said solution is not contaminated. The Nernst equation of the EMF. E5, developed in the reference electrode, is the one you can see on the screen. The pH measurement with the glass electrode is reduced to measuring a resulting potential between the electrodes E1 minus E9 with a considerable internal resistance. To this extent, there may be some difficulties, which I will talk about in the second part of this topic. And well, this will be all for today's video. Don't forget to give me a like, subscribe, and share. I upload videos every Wednesday in Spanish and every Friday in English. Adiós!